Good morning. In the previous classes, we have discussed about non-inverting configuration, also known as voltage series feedback amplifier, and the inverting configuration, also known as the voltage shunt feedback amplifier. Both of them we have derived the expression for gain with feedback, input resistance and output resistances with feedback. And in the first case, non-inverting amplifier or voltage series feedback amplifier, we showed that the gain with feedback is equal to 1 plus Rf by R1 in the approximate case, or if we want the exact expression, the gain with feedback would be what? A divided by 1 plus AR1 by R1 plus Rf. This was the exact expression for gain which we got in the voltage series or non-inverting configuration. But normally we don't use this in our regular design. We will approximate it considering second term is larger than 1 in the denominator. So we will remove 1 and we'll get the expression for gain with feedback as 1 plus Rf by R1 in most of the practical op-amps based non-inverting amplifier. That's how we use. We also showed that the input resistance of the non-inverting amplifier increases with feedback. We showed RIF is equal to Ri into 1 plus A beta in a non-inverting amplifier. So please remember this fact that input resistance increases with negative feedback in a non-inverting amplifier and the output resistance decreases with negative feedback. We could show that ROF would be R0 divided by 1 plus A beta in a non-inverting amplifier. Okay. So we get the ideal conditions needed for a voltage amplifier in this non-inverting op-amp amplifier. And it's called non-inverting because the input signal is fed to the positive or non-inverting terminal of the op-amp. Okay. So remember these things. Then we spoke about the voltage shunt feedback amplifier or the inverting amplifier configuration. In the inverting amplifier also, the gain reduces with feedback and the exact expression for gain with feedback is minus ARF divided by AR1 plus R1 plus RF, as we can see here. We have derived the expression for gain with feedback like this. This is the exact expression. But again, if we consider the factor that what? AR1 in the denominator is much greater than R1 plus RF, then I can remove the other two resistors R1 plus RF from the equation. So I'll have the approximate gain, the gain with feedback AF as simply minus RF by R1. So this is the approximate expression for gain in a inverting amplifier. And we derived it using the simpler method, that is using the principle of virtual ground. And input impedance of an inverting amplifier, we used Miller's theorem to divide the impedance seen connected between the input and output terminals into one part on the input side RF by 1 plus A and another part on the output side RF into A by 1 plus A. So once we do this division, we are able to find the total effective input resistance after applying feedback would be R1 plus Ri parallel RF plus divided by 1 by A. But in this parallel combination, we know that what? RF by 1 plus A will result in a very small value. When compared to Ri, the input resistance of an op-amp, RF by 1 plus A would be very small. And this whole combination will be, parallel combination is always lesser than the smaller value. And even after that, this RF by 1 plus A would be much less than R1 also. That's why we'll say that approximately the input resistance of An inverting amplifier will simply be equivalent to its resistance which we connect to the non-inverting terminal. The resistance which we connect between the input signal generator and non-inverting terminal, that is R1. So please remember this. Output resistance is same as inverting a non-inverting amplifier. Here also the output resistance decreases by the factor 1 plus A beta because of application of negative feedback. Till here we completed in the last class. If you have any doubts, please ask now. If there is nothing, I'll continue with the next topic. Discuss why and how bandwidth increases with negative feedback. So one important advantage, as you can notice here. So what we have many advantages. Sorry. Yeah, we have many advantages of negative feedback. The first one is bandwidth increases. Whenever I give negative feedback in an amplifier, its bandwidth will surely increase. And next is input and output resistances can be changed. So input resistance with feedback will be usually, in most of the cases, we can make it higher than input resistance without feedback. Output resistance with feedback can be made less than output resistance without feedback. These are some of the important advantages of giving negative feedback. And also, the noise or distortion in a circuit will reduce whenever I give negative feedback in the circuit. And one thing you should remember, as a standard rule, anything which decreases, okay, will get divided by the factor 1 plus A beta. And anything which increases will increase or get multiplied by the factor 1 plus A beta. So whenever I say something decreases, you have to divide the earlier value by the value 1 plus A beta. Say for example, all this is obtained at what cost? Which is the only main factor which is a loss for us in negative feedback circuits. What am I losing if I have to get all these advantages? Yes? Gain, exactly. Gain with negative feedback is always gain without negative feedback divided by the factor 1 plus A beta. It's very easy for you to remember these formulae. So anything which decreases should be divided by the value 1 plus A beta. Anything which increases should be multiplied with the value 1 plus A beta. So if I say RIF increases, it will be RI into 1 plus A beta. If I say ROF is decreasing, it should be R0 divided by 1 plus A beta. If I say noise decreases, it is earlier noise divided by 1 plus A beta, something like this. Okay. So let's see how this happens and why. So the open loop voltage gain falls by 20 decibels per decade whenever frequency increases from 100 Hz to 1 kilohertz. You can see this range from 100 Hz to 1 kilohertz. The change in gain will be, if we have marked these points, from 80 decibels to 60 decibels. We have the midband gain plotted in decibels along the y-axis and frequency in hertz in the x-axis, right? And this is a semi-log graph sheet. You can see there is a change by a factor of 10 for each equivalent division on the x-axis. The change is by a factor of 10. Okay, so we are expressing frequency. Each unit here is 1 decade. Yes or no? 1 decade indicates a change in frequency by a factor of 10. So whenever I change from 100 Hertz to 1 kilohertz, it is 1 decade. Okay. So remember that 1K to 10K, again from here to here is 1 decade. And along the y-axis, 1 unit is taken as 20 decibels. Minus 20 to 0, 20 decibels change is there. From 20 to 40, 20 dB change is there. So on. Change in gain along the y-axis, change in frequency along the x-axis. Frequency change is in decades by a factor of 10 and the gain change is in 20 decibels by a factor in decibels it is indicated. Okay. Now you can notice this is the frequency response of an ideal op-amp. The op-amp, ideal or practical op-amp, has a frequency response which looks like this. And you can easily see that though we say op-amp should give us high gain, it gives us very high gain only at some low frequency range. So it gives you a gain of 100 decibels only from 0 to 10 hertz, as you can see. After that, it's again falling constantly. So actually nobody uses any amplifiers within 10 hertz range. Yes or no? So we have to consider the fact that the gain of a practical op-amp decreases as frequency of operation increases. Even if I am operating at 1K or 10K, I have a gain of only 60 decibels or 40 decibels, not more than that for an op-amp. Though we say op-amp is a high gain amplifier, we can't consider such high gain at the frequencies of operation what we consider. Okay. And you can notice that the change in gain here is by a factor of 20 decibels for a change in frequency of 1 decade. Okay. So I can say the rate of change of voltage gain is 20 decibels per decade in the range of frequency from 10 Hertz to 1 kilohertz. Everywhere it is almost the same. This gain bandwidth product of a single break frequency op-amp is always constant. One more thing, in any amplifier you remember, not just op-amp, has its gain bandwidth product always as a constant value. So the product of its gain into bandwidth should remain the same. If I take the gain at this point and the bandwidth, whatever product I'll get, if I find the gain at a different point and the bandwidth, I should get the same value. So wherever on this curve you find the product of gain into bandwidth, it should remain the same. Okay. For any amplifier that is true. And when I say it is an op-amp with single break frequency, we mean it's 3 dB frequency where there is only 1 dB. You see, this is like an RC low pass circuit. It is constant at some range after which the value starts decreasing. This point where the value starts decreasing is known as its break frequency or corner frequency. So the break frequency of this op-amp is 10 Hertz. After till 10 Hertz, it is almost constant. After 10 Hertz, it starts decreasing at the rate of 20 decibels per decade. Okay. So the point where the gain stops remaining constant and starts decreasing, we call that as the break frequency. And whenever there is a single break frequency, that means only once this gain changes. If I say there are two break frequencies, you remember initially when we considered the frequency response, we had considered the Bode plot. So the gain can be like this. One break frequency, the gain falls at the rate of 20 dB per decade. If there is a second break frequency here, the gain will fall by another 20 dB, 40 dB per decade. If there is a third break frequency, again the gain falls by another 20, 60 dB per decade, so on. So since it is all falling, you see at each point where there is a change in the slope of this curve, we say there is a break frequency which is occurring. So if there are multiple break frequencies, this will happen at many points. We saw actually with respect to this curve in the frequency response of amplifiers. So since the gain with feedback is less than gain without feedback, the bandwidth of the amplifier should surely be larger than that without feedback. Why? Because of the factor that gain bandwidth product should be constant. Because this should remain constant in feedback circuits. In feedback circuits, if the gain with feedback decreases, then bandwidth with feedback should increase so as to maintain what? Constant gain bandwidth product. The product of gain into bandwidth should remain constant. So if we say that one of the factors decrease, the other factor should automatically increase to maintain constant gain bandwidth product. Okay. Now coming to this representation of this bandwidth of the amplifier with feedback, you see the same curve like what we wrote before is written here, and the actual gain value at this point will be 2 into 10 to the power of 5, which turns out to be 100 dB. If I write it in decibels, this would be 100 dB, but otherwise it is 2 into 10 power minus 5 if I don't write it in decibels. And you see the break frequency occurs at 10 Hertz or 5 Hertz. Usually it will be nearing 5 to 10 Hertz. Depends on the device. Okay. And as usual, after the single break frequency, the rate of change of gain is minus 20 decibels per decade. For every decade of frequency change, say from 1K to 10K, 10K to 100K, so on, for every decade of frequency change, the gain will fall by 20 decibels per decade. Okay. So what is the value of, who has unmuted? What's the value of this unity gain bandwidth product? So let's take the bandwidth when gain is 1 as 1 megahertz. Okay. UGB or unity gain bandwidth product, the definition is it represents the bandwidth of the circuit when the gain is 1, or bandwidth of the op-amp when the gain is 1. So when is the gain 1? You see here the gain of the op-amp has come to 1. From 2 into 10 to the power of 5, the gain has reduced to 1 at this point. The corresponding frequency matching this when the gain has come down to 1 is 10 power 6. So here 10 power 6 represents the unity gain bandwidth product. Okay. So the unity gain bandwidth product is a measure of what is the bandwidth of an op-amp when its gain reduces to 1. Okay. In this case, we can see it is product of A into F0. If I call this point as F0, A into F0, which is going to turn out to be how much? Here it is 1 into 10 to the power of 6. So the gain is 1. The gain is 1 and bandwidth is 10 power 6. So I'll have a value 10 power 6. Similarly, if I try to find the gain bandwidth product at this point, you see this point is at 5 Hertz, right? And the corresponding gain is 2 into 10 power 5. So 2 into 10 power 5 into 5 Hertz. will again give you a value 10 power 6. Okay. So either way, wherever you find along this curve the gain bandwidth product, it should remain the same. So consider the amplifier with gain AF and bandwidth FF. Then AF into FF should be equal to A into F0, which is the unity gain bandwidth product. So please make a note of this. The gain bandwidth product is found at any point on this curve. If I find it at this break frequency or the corner frequency, we call it as. At this point, the gain is maximum A and the bandwidth is minimum. You can see the bandwidth is only 5 Hz. Bandwidth is only from here to here in this case. Gain is high but bandwidth is very low. So it has very little usage in that range. Supposing I want to go for a higher bandwidth but less gain is okay for me, I can use this point where the bandwidth is 10 power 6 megahertz but the gain is 1. Now let's try to define this for non-inverting and inverting amplifiers. We already know that in a non-inverting amplifier, the gain with feedback is gain without feedback divided by the factor 1 plus A beta. This is constant for any feedback amplifiers. Wherever we use negative feedback, this factor will remain unchanged. Okay. And next, let us define this, the bandwidth. Either I can call it as FF or you call it BWF. See why we are calling it FF? Because here when I talk about bandwidth, it's usually what? The difference between two frequencies. At this point we are calling the frequency as FF and at this point it is 0. So the total bandwidth in this case is FF minus 0, which is FF. Okay. Since one end is at 0 for the op-amp frequency response characteristics, we can always consider its bandwidth as the higher cutoff frequency of the amplifier. And this amplifier higher cutoff frequency is indicated as FF. Therefore, the bandwidth is equal to what? A times F0 divided by FF. The bandwidth with feedback is nothing but, I know what is this AF0. This AF0 represents the unity gain bandwidth product. Please remember, in the previous slide we have shown what is unity gain bandwidth product. You see UGB, unity gain bandwidth product, is nothing but the product of the gain into the frequency F0. So F0 represents this frequency. Product of gain at that point is A. So we have A into F0 as the UGB, unity gain bandwidth product. I have to substitute that and divide it with AF to find the expression for bandwidth with feedback. And this should be surely equal to the value bandwidth without feedback F0 into 1 plus A beta. F0 represents the bandwidth without feedback F, okay, and A is the gain of the op-amp amplifier and B is the gain or transfer function of the feedback network. Please remember this. I told you when something increases, it gets multiplied. The same equation I can write it as bandwidth with feedback is bandwidth without feedback into 1 plus A beta. Even if you write it like this, it is fine. Okay. So what you should remember, FF is nothing but unity gain bandwidth product divided by AF. Here you can see clearly this FF is the UGB, unity gain bandwidth product divided by AF, which turns out to be of the value F0 into 1 plus A beta. Okay. So whenever gain decreases, the bandwidth should increase. That's another logic which we have applied. For the inverting amplifier, the gain with feedback is given as A into K divided by 1 plus AB. So what is this K? K represents an attenuation factor which is added or multiplied with the basic gain with feedback. So you can see that it's the same equation but just with an additional multiplication factor of K. Therefore, bandwidth with feedback is equal to bandwidth without feedback into 1 plus A beta. Okay. Either of the cases, whether it is non-inverting or inverting, the bandwidth with feedback is always bandwidth without feedback into the factor 1 plus A beta. Please remember that. So it's a clear-cut case telling that the bandwidth increases whenever we apply negative feedback in the circuit. Okay. And we have something called as the transition frequency, Ft. That Ft is the product of unity gain bandwidth into a ratio K divided by the value AF. So this value K, the attenuation factor what we have, that should get multiplied with the unity gain bandwidth product and then divided by the factor AF. Okay. Hence, you can clearly see that I'm just substituting for the value of what? Just substitute for the value of this A everywhere. In this form, you'll get AF is minus AF of the non-inverting amplifier into the factor K. Anyway, I think this part is not essential. What you need to remember is just you have to write the equation for bandwidth, telling bandwidth with feedback is always higher than bandwidth without feedback by a factor 1 plus A beta. You see the standard expressions for voltage gain for non-inverting as well as inverting amplifier, and then the standard expression for what? Approximate value of the voltage gain, and then the feedback factor, input resistance, output resistance, the bandwidth FF is F0 into 1 plus A beta, and the bandwidth in terms of the unity gain frequency. Okay, here unity gain frequency by AF, and finally we have something called as output offset voltage. Can somebody define what is output offset voltage in an op-amp? You have studied this. What are offset voltages? What are offset voltages in the context of op-amp? Yes? You should answer fast. You know or don't know?
And voltage to be applied at inputs to make the outputs zero.
Okay, voltage that should be applied at the input to make output zero. That is called input offset voltage, right? What is output offset voltage? It is the voltage which is present at the output irrespective of both the input terminals being grounded. I showed you the case other day. Though both the input terminals are connected to ground, there is a chance that, and there is always the possibility that there will be some output voltage which is not 0. Ideally speaking, without any input, the output should have been 0. But because of the mismatch between the transistors which make the building blocks of op-amp, there is always a chance that irrespective of both the inputs being 0, the output will tend to have some value which is not 0. And that error voltage which appears is called the output offset voltage. Anyway, the offset voltage values we'll talk a bit later. Can you solve this example? Please write down fast. In a non-inverting amplifier, given A is 2 into 10 to the power of 5, Ri is 2 mega. So let me write what is given. A is 2 into 10 power 5, Ri 2 mega ohm, and R naught 75 ohm, and F naught 5 hertz. So this is the initial bandwidth, which is 5 hertz. The supply voltages are given from plus or minus 15, and output voltage swing is only plus or minus 13. So even if we are giving 15 volts, the device saturates at plus or minus 13. Okay. The devices inside the op-amp will saturate at this value. It won't it'll reach hardly 80% of the peak. Now, if R1 is 1K, RF 10K, calculate the values of AF, RIF, ROF and FF. Do it. You have to find it using exact equation and the approximate. Already the formulae are written. AF is A into R1 plus RF divided by R1 plus RF plus AR1. This is the standard expression for gain in a non-inverting amplifier. Right? You remember we wrote that as AF as A divided by what? AR1 plus R1 plus RF. Same equation. Okay. Can you find out and let me know all the equations I have given? I just want you to find the exact value and also the approximate value so that we'll be able to see the difference. How much difference will actually be there between exact and approximate value we can analyze. Please do it fast. Substitute everything. This A is 2 into 10 to the power of 5. R1 1K. RF 10K. R1 plus RF 11K plus A into 1K. This is a huge value. So what would you get in the numerator? You check. Any answers? And calculate the approximate value also. This is easy. 1 plus RF by R1. 1 plus 10 by 1, you will get 11. So the approximate value of gain turns out to be 11. Can someone tell me what is the exact value you're getting?
10.99.
10.99. So you can see how much difference is there between the two. That's why it hardly is important for us to do the exact calculations, and exact equation need not be used in the design. There's a 0.01 or hardly less than 1% error. So it won't matter. The others you calculate. Input resistance with feedback is input resistance without feedback, which is 2 mega into, it would always be helpful if you calculate this value 1 plus A beta. A is 2 into 10 power 5 and the feedback factor, is it given? No. How do you find the feedback factor beta? Do you remember the equation? R1 by R1 plus RF. Find it. The feedback factor B or beta is given as R1 by R1 plus RF. It is 1 divided by 11. How much would that be? Find out RIF, ROF. That's why I told for all the three cases you need the value 1 plus A beta. So find this first. 1 plus gain into beta. The feedback factor beta is 1 by 11. 0.09.
3.636 into 10 power 10.
Oh, that's what I'm asking. It can't be in mega, it is larger. Into 10 power 10, or in other words, I can say it is 36.36 giga ohm. 36.36 giga ohm. Okay. And what about this? ROF. RO is given as 75 ohms. So 75 divided by, how much is 1 plus A beta? 1 plus A beta also.
4.12 milli.
Milli.
Yes, ma'am.
4.12 milli ohms. You just have, I hope you got an idea by what extent the output impedance is reduced. So it is almost making the output resistance of the device look like it is zero. We hardly are bothered for any resistance which is in milli ohms. Yes or no? And what about the input resistance? Input resistance appears like it is infinity. Look at 36.36 giga. It's a resistance which is in the range of 10 to the power of 9 or 10 to the power of 10. Too high. It almost appears like infinity. Very large input resistance, very low zero output resistance. Comes closer and closer to ideal device, ideal amplifier. And bandwidth, have anybody calculated FF, the bandwidth? F naught into 1 plus A beta. This F naught is 5 hertz. Just multiply it with the value 1 plus A beta. You will get the bandwidth with feedback.
91005.
Okay, 91 hertz.
Yes, ma'am.
Okay, it is 91 kilohertz. You have 91005 hertz, or in effect the bandwidth is 91 kilohertz. This is because, and you observe the difference again. The bandwidth of the amplifier without feedback was just 5 hertz. Something which was 5 hertz has been converted to 91 kilohertz. It's such a huge change. So you have a factor which is in 5 hertz being converted to something which is 91 kilohertz. Then it is a really big change which is done. And do it for this problem. Write down this problem. It's an inverting amplifier. Given A is 2 into 10 power 5. Ri 2 mega, R naught 75 ohms, F naught 5 hertz. Everything remains the same except R1 and RF values have changed here. Compare the exact and ideal values. I have written the equation for, and remember, usually in problems, if it is asked for something more than 5 marks or more, you have to draw the diagram. So diagram of the inverting amplifier, write all the equations correctly because equations will carry half the marks. Your computation will carry 1/2 of the marks and equations the other half. At least even if you are wrong in computations, you should get the marks for writing the equations correctly. Please calculate all this. By exact method, what is the gain with feedback? Minus ARF by R1 plus RF plus AR1. So that's why we call this as minus A into K by 1 plus A beta, where K is RF by RF plus R1. This is the value of the feedback factor K. Ideally, you will get how much? 4.7 K by 470 ohms with a minus sign. This is 10. Ideal gain or practical gain is minus 10.
Minus 9.77.
Okay, minus 9.77 is your exact value, and you are assuming it to be minus 10. Naturally, this minus 9.77, when we approximate, it will be, this is more than 0.5, the decimal place, so easily we can consider it as minus 10. That's why our approximate derivations hold good correctly. Beta value is as usual R1 by R1 plus RF, which is 470 divided by 470 plus 4.7 K. Check out how much is the beta value, and then you check the others. All the formulae are written. I want you to compute RIF exact value and match it with what is RIF approximate. In the inverting amplifier, I told you, remember the input impedance with feedback is equivalent to the resistance which is connected between the voltage signal generator and the inverting terminal. So approximately RIF is equal to R1. Exactly RIF is R1 plus some factor. I want you to calculate approximate value and the exact value. Approximate, there is no calculation. It is just RIF is 470 ohms. I want you to find how much is the exact input resistance using this relation. Please do it. And find R0 and FF. All of you do it and post your answers on the chat.